Уважаемые коллеги, я, пожалуй, начну заново. Значит, скажу о том, что действительно с именем Ивана Георгиевича Петровского самым тесным образом связаны Московский университет и механико-математический факультет. Хотя мы знаем, что по первоначалу ученик Егорова Дмитрия Федоровича работал в Саратовском университете вместе с другими учениками, значит, и Иван Иванович Привалов там работал, Степанов, вот, и другие более старшие ученики Дмитрия Федоровича Егорова. И так получилось, что в 1940 году Иван Георгиевич Петровский был избран деканом механико-математического факультета, и с этих пор его деятельность самым тесным образом связана с Московским университетом. Значит, ну, самое трудное – это, конечно, годы войны. Механико-математический факультет был эвакуирован в Ашхабад, а потом из Ашхабада в Свердловск. Но самое интересное, что занятия здесь, ну не вот прямо в этом месте, а там, где находился Московский университет, продолжались в Москве. Вот, и здесь работали и Колмогоров, и Павел Сергеевич Александров, они приезжали из Казани, и вот эта работа осуществлялась. И прежде чем сказать об этих трудных годах, когда Ивану Георгиевичу Петровскому пришлось как бы удерживать факультет на том уровне, который был, вот, мы должны понимать, что в этом случае было очень трудно. Значит, надо было ездить из, скажем, Свердловска в Москву, здесь смотреть, как происходят дела из Москвы в Свердловск и многие другие вот вещи. Но Ивану Георгиевичу удавалось это сделать, и действительно удалось сохранить факультет в первую очередь. В 1943 году Иван Георгиевич был избран членом-корреспондентом Академии наук, в 1946 году он стал академиком, и, значит, в 1943 году он стал исполнять большие обязанности по Академии наук. Но надо сказать, что в том же 1943 году, это самый такой напряженный момент Великой Отечественной войны, там было правильное понимание того, как надо заниматься наукой. Вот я хотел бы сказать, что и мы должны, хотя сейчас у нас не военное время, но понимать, как это было. Вот Павел Сергеевич Александров вспоминает, что было собрание Академии в Казани, где выступал вице-президент Академии наук Отто Юльевич Шмидт. И он, конечно, сказал, что да, время военное, и мы, конечно же, должны работать на оборону нашей страны, на военную промышленность. Вот. Но, говорит, а все-таки теоретические исследования не должны прекращаться, но только они не должны быть не пустяковыми, а настоящими теоретическими исследованиями. И это, конечно же, подбодрило многих, и в частности, конечно, вот эти воспоминания Павла Сергеевича Александрова. Он как занимался топологией, так он и продолжал этим заниматься. Это действительно как бы такая опора была. Но вот второй момент, и это, собственно, завет, который нам оставил Иван Георгиевич Петровский, он состоит в том, что математика едина. Он сам занимался многими вопросами в математике. И это очень важно, что действительно такое понимание того, а что делается в математике, что можно сделать в математике. И вот это то, что действительно нам должно помогать. Но и третий момент, о котором я хочу сказать, что действительно должно быть всеобщее понимание востребованности математики. Если нет этого понимания, то это очень плох. Вот мне приходилось бывать в многих периферийных вузах в нашей стране. И когда начинаешь обсуждать проблемы, я говорю, а зачем нам Мехмат Московский университет? Мы сами можем подготовить своих специалистов. Ну и все. На этом мы должны понимать, что на этом все может и закончиться. То есть ту высокую планку, которую задает, скажем, хотя бы один университет, ее не будет, она будет падать. Даже если хороший специалист, но он один там, и ему действительно будет очень и очень тяжело. Вот. Конечно же, мы собрались для того, чтобы обсуждать научные проблемы. Проблемы теории дифференциальных уравнений, математической физики. И, безусловно, это те моменты, которые дают возможность говорить и о приложениях математики. И тем и была сильна в свое время, я думаю, и сейчас, кафедра дифференциальных уравнений. Ну что же, пожелаю успехов нашей конференции, чтобы эта конференция была праздником для всех математиков. И здоровья, будьте здоровы.
So, dear colleagues, I'm quite happy to welcome you to this conference. As you know, the Petrovsky conference was the main meeting in differential equations and related topics, maybe since 70s and during 80s and during the beginning of 90s. That time, this conference was annual, and the people from the Soviet Union and then from Russia and other countries came here to Moscow University, and exchanged their knowledge concerning differential equations and many related topics. Then it became quite difficult to organize this conference each year, and the conference occurred more and more seldom. But now it appears again, and I hope that it will be regular in future. So you are welcome to this conference, and let's start our scientific program. So now I will come to the mathematical part of my talk. My talk will be devoted to the asymptotical theory of differential equations, namely to the semi-classical asymptotic theory for partial differential or pseudo-differential equations which contain singularities in coefficients. To be more concrete, I will consider the equations which contain singularities of delta type or of type contain some discontinuous functions, or some functions which come to delta functions or discontinuous functions in a weak limit. So this is a joint work with Anna Alliluyeva and Olga Chigartsova, and here is the outline of the talk. So first of all, I will remind the very well-known theory which describes semi-classical asymptotics for equations, differential or pseudo-differential evolutionary equations with smooth coefficients. And I will concentrate on geometrical objects which appear in this theory and which describe intrinsically the solutions of the corresponding Cauchy problems. These geometrical objects are Lagrangian surfaces in classical phase space, and also some complex vector bundles which are called Maslov complex germs. Yeah? And then I will pass to the main part of the talk, to the description of asymptotic solutions for equations which contain singularities. The program of description of such asymptotics is now starting. So we have only some first examples of what happens with these geometrical objects when we have singularities in coefficients. And I will speak about two main examples. One of them is Schrödinger time-dependent Schrödinger equation with delta potential, and another one is the wave equation with some singularity in the velocity. Okay. So first of all, I will remind the general theory of short wave or semi-classical asymptotics for evolutionary equations with smooth coefficients. So here is the equation itself. H here is some pseudo-differential operator, and here h of xp is the smooth symbol of this pseudo-differential equation, which is the smooth function in R to n. And for this equation, let's consider the Cauchy problem of the following form. So this is the short wave or semi-classical type of the initial conditions. And the problem is to describe the asymptotics of the solution of this Cauchy problem in the limit as epsilon tends to 0. Okay. If we consider this initial condition, then generally speaking, the behavior of these functions can be different if this initial phase S0 is real or complex. So first of all, if this S0 is real, then we have some rapidly oscillating function, so like wave packet, and the problem is to describe the evolution of this wave packet. Then the asymptotic solution is described in the following way. It is a very well-known fact. First of all, we have to consider the classical phase space R to n with coordinates x and p. And in this phase space, we have to consider initial surface, which is defined by these equations. P is the gradient of the initial phase. This is the Lagrangian surface. And then we have to move to shift the surface along the trajectories of the classical Hamiltonian system, which is written here. This Hamiltonian system is defined by the symbol of the initial pseudo-differential operator. Okay? So we obtain the Lagrangian surface lambda t, the shifted initial surface. And on this surface, we have to define the volume form. The volume form is defined in a quite natural way. We consider the volume form dx on the initial surface, and then again shift it along the trajectories. Okay? So this geometric object, lambda together with the volume form, describe the asymptotic solutions. So the theorem, which belongs to Maslov, it was proved about in 60s, that under certain technical conditions on the symbol of the operator, the asymptotic solution of the Cauchy problem can be represented as asymptotic seria of the following form. Here, K denotes some analytical tool which was constructed by Viktor Pavlovich Maslov, and it is called Maslov canonical operator. This tool makes it possible to, so formally it is some operator from the space of smooth compactly supported functions on this Lagrangian surface to the space of smooth functions on coordinates x, and depending on coordinates x. And so this is some tool which makes it possible to construct such rapidly oscillating functions. So we have to apply this operator to some asymptotic seria, and the main term of this asymptotic seria, again, is very simple. We have to consider initial amplitude. So phi naught here is the initial amplitude of the wave packet, and shift it along the trajectories of the corresponding Hamiltonian system. Okay. Now, if the initial phase is not real but complex, then the situation is more or less similar, but instead of this Lagrangian surface, we have to construct some more sophisticated geometrical object, which is called Maslov complex germ. So let's suppose that the initial phase is complex. Then we have some sort of squeeze state. So we have some function which oscillates in the direction of in certain directions and rapidly decays in other directions. So here are more strict conditions on the initial phase. So let's suppose that it is complex. The imaginary part is non-negative, and it vanishes on some smooth surface, on smooth k-dimensional surface W naught. And in the normal directions to the surface, the second derivative of the imaginary part of the initial phase is positively defined. Okay? Then we have again to construct some geometrical object. This geometrical object is following. First of all, we have to consider the k-dimensional isotropic surface lambda naught, which is defined by the following equations. So x here is the point of this k-dimensional surface. And we have to supply this k-dimensional isotropic surface with the fibers. So we have to construct some complex vector bundle, which is called Maslov complex germ. So fiber in the point X and P is defined by the following simple equations. So we have n-dimensional complex vector bundle over k-dimensional real isotropic surface. And then we have to do just the same. We have to shift all of this along the trajectories of the classical Hamiltonian system. So the surface itself is shifted with respect to the phase flow, and the fibers of this bundle are shifted by the differential of the corresponding flow, of course. Okay. And again, this theorem is also a theorem which belongs to Viktor Pavlovich Maslov, that under certain technical conditions, the solution can be represented in the asymptotic series of this form. Just the formula is more or less the same as this one, only instead of Maslov canonical operator on Lagrangian surface, we have to consider some other technical tool, which is called Maslov canonical operator on the complex germ. So it is some analytical tool which again associates with any smooth function on the isotropic surface, the smooth function of coordinate axis. Okay? And again, the main term of asymptotics is defined by this simple formula. So simply we have to shift the initial amplitude along the trajectories of the Hamiltonian system. Here are the explicit formula for the simplest case. Of course, the simplest case in this situation is when the initial surface W0 is just a point. So we have some type of Gaussian beam, the function which is localized in the small vicinity of a point. So let's suppose that W0 is a point, and let's suppose that the initial phase is the quadratic function of this type. So Q0 is the complex matrix with positive imaginary part, symmetric matrix with the positive imaginary part. Then the formula for the Maslov complex germ, for the Maslov canonic operator on the complex germ is very simple in this case. It's just some exponent with complex phase as S multiplied by the asymptotic series of this type. And the complex phase also has a very simple form. We have to consider the trajectory of this classical Hamiltonian system and substitute in the initial phase, instead of these constants P0 and Q0, just the trajectories of this Hamiltonian system. And the matrix Q is defined by the linearized system. It is constructed from the solutions of the corresponding linearized Hamiltonian system. Okay. Now the main problem which I would like to discuss, what happens with these geometrical objects, Lagrangian surfaces and complex germs, if we deal with equations which have singularities. So first example will be the Schrödinger time-dependent Schrödinger equation with delta potential. So this is the equation of this type. I will suppose that V is a smooth function which satisfies again certain technical conditions. And here we will add some delta potential which is localized on a smooth oriented hypersurface in n-dimensional Euclidean space. Formally, it means that we have to do the following. We have to consider this Laplacian in n-dimensional space. We have to restrict this Laplacian to the functions which vanish on this surface and take the self-adjoint extension of the corresponding operator. More practically, it means that we have to consider this equation this equation without this delta function in the semi-spaces which are defined by the surface. So the surface divides the space into two semi-spaces. And we have to supply this equation with these boundary conditions which define this delta function in the operator. So Q is some smooth function on the surface M. Okay. So formally, we are solving this problem. And I will now describe what happens with the geometrical objects which define the asymptotic solutions in this case. Something is. Mm-hmm. So First of all, I will consider the case of real initial phase. So let's suppose that this function S0 is real. Then the main idea is that we have to construct some Lagrangian surfaces which describe here transmitted and reflected waves with respect to this hypersurface M. Here is the formal construction. First of all, we have to consider the extended phase space. We have to add here the time t and the dual coordinate p0. And in this phase space, we consider the isotropic surface, which is defined by these equations. So we consider the standard equations and supply it by the equation h equals to 0, where h is the symbol of the smooth part of this operator, together with this term which is derivative with respect to t. And then again we construct the Lagrangian manifold, shifting this initial isotropic surface with respect to the trajectories of the Hamiltonian system, corresponding to this smooth Hamiltonian. So we take the union of all shifted surfaces and define the surface of dimension n plus 1. Lambda naught is the surface of dimension n, and lambda plus is the surface of dimension n plus 1. And then we have to reflect the surface. The reflection is quite natural, the most natural as one can imagine. So first of all, we have to consider the surface, which is the support of the delta function, and we have to shift the surface to the phase space. Just take the surface, which is defined by the same equations. And we have to intersect the surface with this lambda plus. Here we must, of course, write lambda plus. And then consider the tangent and normal components of the momentum p in the points of this shifted surface. Now we construct the reflected surface in the following form. So we replace the normal component, we change the sign of the normal component of the momentum. So using this map Q, we obtain from this hypersurface M the hat n plus another hypersurface n minus, and then shift it again along the trajectories of the Hamiltonian system. So we obtain the reflected Lagrangian manifold. So we have two manifolds, lambda plus and lambda minus, which correspond to transmitted and to reflected waves. In order to construct canonical operator, we also have to define the volume form. The volume form is defined also in a very natural way. We consider the initial volume form of this type, construct the invariant with respect to the Hamiltonian flow volume form on the lambda plus, which just has the following form. S is the time, the proper time along the trajectories of the Hamiltonian system. And then substitute in this form the normal component of the momentum, map this form to n minus, and again construct the invariant form by this rule. So we have the invariant forms on both manifolds lambda plus and lambda minus. And now in one hyperspace we consider this formal series, and in another this one, when the functions are the main terms of asymptotic solutions have the following form. So here the coefficients which are written here, here Pn is the normal component of the momentum, and Q is the factor which enters the delta functions. So these coefficients play the role of transition and reflection coefficients in this situation. Okay? Now the theorem is that for any finite time interval, the asymptotic solution of the Cauchy problem has the following form. These series are asymptotic for the solution of the Cauchy problem. Okay? Now I will say just by words what happens if we consider the complex phase. Then we have to, in addition to the definition of the reflection of Lagrangian surfaces, we have to define the reflection of fibers of complex vector bundles. The fibers are reflected with respect to the following rule. So the fibers are complex Lagrangian planes. We can identify each such plane with the complex valued quadratic form on the n-dimensional space, on the tangent space to Rn. Then the reflection has the following form. If we consider the value of this quadratic form on the tangent space to the surface, which is the support of the delta function, then on the tangent plane to the surface, it is shifted by the second fundamental form of the surface. And if we consider it on the pair normal vector and tangent vector, then it is shifted by the derivative of the potential, of the smooth part of the potential. Okay. Now the second example which I will describe is the wave equation. In this case, I will consider not honest singular function, but some function which has singularity in the weak limit. So I will suppose that the velocity in this wave equation singularly depends on this small parameter epsilon. Here phi is the smooth scalar function, and this equation phi equals 0 defines a smooth regular hypersurface in Rn. Okay. And I will suppose that this function c is strictly positive, smooth, and tends to limit as this rapid variable tends to plus and minus infinities. And these limits are different, c plus and c minus. And again, I will suppose the initial conditions of this rapidly oscillating time. Okay. Here is the picture which illustrates the behavior of the velocity. So velocity has a rapid jump near some hypersurface. And we consider the initial wave packet which comes to this surface of the rapid jump. The weak limit of this function as epsilon tends to 0, of course, is the Heaviside function corresponding to the surface M. If we consider the particular case when C plus and C minus coincides, then we have some peak near this function M. Then if we divide this function by epsilon, then the weak limit will be a delta function. Okay. So now I will describe the type of asymptotic solutions for these equations. So I will start with the one-dimensional case. In one-dimensional case, the formulas are quite explicit. So let's suppose that x is one-dimensional and m is a point. So the function phi is the linear function of this type. First of all, I will remind what happens when we don't have any rapid dependence on the velocity on epsilon. So let's suppose that the velocity is the smooth function independent on epsilon. Then asymptotic solution has the following form. It represents two waves. One of the waves comes to the right and another one comes to the left. Of course, this formula are very well known. They are in the handbooks. The formulas for the phases and for amplitudes are quite explicit. So here are these formulas here. Okay. And all the corrections also can be expressed by explicit formulas using the previous amplitudes. Okay. Now, if we consider the rapidly varying velocity, then during some time, when the time is sufficiently small, then the solution will have the same form, because the initial wave packet doesn't reach this point where we have the point x naught, where we have the rapid variation of the velocity. But if we consider some more large times, then we have to construct again reflected and transmitted waves. In this case, in order to construct these waves, we have to consider some second order differential equations of this type. Here V is defined by the rapidly varying velocity here. And consider the solutions of these equations, which are some sort of Yost function. So we have, for this equation, we have a solution which with the following behavior, as this variable y tends to minus infinity, it is sum of this exponents, and at plus infinity it is one exponent. Okay, here these coefficients r and tau are complex reflection and transmission coefficients, and using this additional second order ordinary differential equations, we can describe the asymptotic solutions of the initial problem. The asymptotic solution will have the following form. So here, the first summand describes the wave which comes to the left, so it doesn't reach the point when we have the rapid oscillation of the velocity. Here, the second summand is the wave which comes to this point, and the third is the transmitted wave, and the last one is the reflected wave. Okay, and all these phases and functions f are defined by quite explicit formulas. Here, all these formulas are written down. I will only indicate that this complex transition and reflection coefficients, which are defined by this equation, they define just the division of amplitudes of transmitted and reflected waves. So it is written here. Okay. Now I will pass to multidimensional case. In multidimensional case, we have two new effects. First of all, the asymptotic solution cannot be represented in terms of exponents only, because we will have focal points, and we have to use these geometrical objects, which are Lagrangian surfaces and so on. So use the Maslov canonical operator. And the second effect is the physical one. If we have certain conditions on the initial phase and on the velocity, then we can have total reflection. So the transmitted wave can disappear at all. Okay. So this is the picture which illustrates this total reflection. If we look from the water to the surface of the water under some angle, we will not see the air which is upstairs, but we will see the reflection of all which is underwater. Okay. So first of all, I will again remind what happens when we have the regular velocity. Then and we have considered the extended phase space. In this phase space, we have to consider the isotropic surface, which is given by these equations. And we have to shift this isotropic surface with respect to the Hamiltonian system and obtain the Lagrangian surface, which is invariant with respect to the Hamiltonian flow. Again, we have to define on this Lagrangian surface the volume form, just in the same natural way. And the asymptotic solution has the following form. Here, K is the Maslov canonic operator on this invariant Lagrangian surface. And again, the main term of asymptotic solution is nothing more but the initial amplitude, which is shifted along the trajectories of the Hamiltonian system. Now, what happens if we consider the rapidly varying velocity? Then, again, we have to construct the reflected manifolds. The reflected manifolds are constructed more or less in the same way as for the Schrödinger equation. We consider these two Hamiltonian systems, which correspond to two limit velocities, C plus and C minus. The limits of the rapidly varying velocity as this variable tends to plus or minus infinity. We have to construct two Lagrangian manifolds, which will be invariant with respect to the trajectories of one system, and another manifold which will be invariant with respect to the trajectories of the another system. So the construction are just more or less analogous to the case of Schrödinger equation. So we shift the surface of the rapid jump of the velocity to the phase space. We intersect the initial Lagrangian surface with this shifted surface, and then define the reflection and the transmission. This reflection and the transmission are defined differently for these different cases. So this case, it means that we have both waves transmitted and reflected. And in this case, we have no transmitted wave, we have only reflected wave. So this condition means that we have this effect of total reflection. Okay? So for these two cases, the maps which define the new Lagrangian surface are different. So for the first case, we have to consider these two maps. One of them changes the sign of the normal component of the momentum, and another one constructs the new momentum of this type. Here we have just this function which is strictly positive. Okay, so this is just the same function. We apply this map to the surface n and consider these two surfaces. N plus will be surface which corresponds to the transmitted wave, and N minus to the reflected one, and then shift the surfaces along the trajectories of the Hamiltonian system. And again, we define just in this natural way the volume forms. We consider the initial volume form, consider the invariant volume form on the surface which corresponds to the initial wave, and then substitute to this form the normal component on the velocity, transfer it to our surface by the diffeomorphisms, q plus and minus, and again construct the invariant volume forms. So after all these operations, we obtain 4 Lagrangian surfaces. 2 are initial, 1 and 2, which describe 2 waves passing into different directions. And surfaces plus and minus, one of them describes the transmitted wave, and another one describes the reflected wave. Okay. In the second case is the case of total reflection. The situation is more simple. We don't have the surface corresponding to the transmitted wave. We have only the surface corresponding to the reflected wave, nothing more. Okay. If we want to define the amplitudes of the transmitted and reflected waves, we have to again to consider this second-order differential equations. The potential is constructed with the help of the velocity here. Okay. When we have both waves transmitted and reflection, then we have again some type of Yost function for this equation. And in the case of total reflection, we have the solution which has the following form. At minus infinity it oscillates, and at plus infinity it vanishes. Okay. And again here we have these coefficients which are coefficients of transmission and reflections. These are functions on Lagrangian surfaces. And the theorem is that the solution of Cauchy problem can be represented in terms of Maslov canonic operators on these four Lagrangian surfaces. For all these functions, f plus, minus, 1, and 2, we have quite explicit formulas. Here some of these formulas are written down. The main point which I would like to mention that the coefficients of transition and reflection for the second-order differential equations define the division of amplitudes between the transmitted and reflected waves on this manifolds lambda plus and lambda minus. Okay. For the second case, when we have total reflection, we have more simple formula. We have only the reflected wave and no transmitted wave. Again, here are the explicit formula for the amplitudes. And as for the solutions with complex phases, again, we have to define the rule of the rules of the reflections of the vector bundles, and the rules are just analogous to the case of Schrödinger equation. Again, we have to identify the complex Lagrangian plane with the quadratic form, complex valued, and on the tangent space to the surface, which is the support of the rapid jump of the velocity. this quadratic form is shifted by the second fundamental form of the surface, and in the normal direction, it is shifted by the derivatives of the function c. Okay. So this is all. Thank you very much for the attention.
Thank you very much. Maybe somebody have questions. Yes.
У вас уравнение Шрёдингера с эпсилоном при производной по t, а вот гиперболическое без. Почему так?
Ну, значит, для уравнений Шрёдингера эпсилон при производной по t это как бы такое его стандартное написание. Тут, наверное, вопросов нет. Почему в уравнении волновом его нет? Ну, потому что волновое уравнение, оно однородное по производным. Если мы его умножим на эпсилон квадрат, просто все умножим, вот у вас и будет ровно эпсилон квадрат при второй производной.
Ну, это же можно сказать и про Шрёдингера.
Не, Шрёдингер неоднородный. У него первая производная по t, вторая по иксам.
Там оператор от эпсилон до x.
Да. Да, ну и в волновом уравнении тоже оператор от эпсилон d по dx. Просто я тут на это эпсилон сократил.
Я догадался,
Да.
я увидел именно различия.
Да. Ну, как бы, сейчас я самый первый какой-нибудь слайд покажу. Ну, мы всегда рассматриваем уравнение такого типа. И волновой, и Шрёдингера, они все такого типа. Вот. Ну, просто в волновом я на эпсилон квадрат сократил. Ага.
А если эпсилон убрать от производной по t, там совсем все меняется?
Да, ну и как совсем меняется? Значит, если тут либо убрать эпсилон, либо поставить вместо эпсилон что-нибудь другое, это просто означает, что мы на других масштабах времени рассматриваем нашу задачу. И, конечно, если мы хотим на очень больших временах рассматривать, все будет совсем по-другому. Если на маленьких, то это все то же самое, только еще проще. Ну, так, ситуация такая. Да.
Андрей Ильич, вы эпсилон устремляете к нулю, но самого взятия предела требует все-таки, наверное, какой-то непрерывности, чего-то вот такого. Если этого нет, в принципе, функции может быть и ограничены вариации, там, и всякие такие вот эффекты, и тогда просто, ну, вот таким приемом вряд ли вы захватите, ну, анализ фурии.
Само собой, нет, ну вообще вот, ну как, тут вот прям вот тут написано, что тут вот эта наука изначальная, которую там придумывал Виктор Павлович Маслов, она вообще для уравнений с гладкими коэффициентами, вот, ну просто гладкими, вообще бесконечно дифференцируемыми. Вот. Ну вот у нас тут какие-то сингулярности появляются простейшего типа. Если мы хотим какие-то совсем общие коэффициенты, там вот, ну типа там ограниченной вариации или там, не знаю, из каких-то классов, это какая-то совсем другая задача. В общем, ну как бы тут... Это задачи такие принципиально матфизические, то есть там как бы в матфизике там все-таки бывает все гладкое, ну бывают какие-то особенности, вот. А так, чтобы там общие классы функций, это редкость. Да, это совершенно стандартная вещь там в матфизике, они ее все время рассматривают. И на поверхности, и в точках, там, и где угодно. Да, конечно.
Okay, thank you very much. Let's thank again our speaker.
Thank you very much.
I would like to say that our chief of our department, Valery Vasilievich Kozlov, is ill, unfortunately, but he sent you his congratulations, and he sent this historical photo. Historical photo. Wait a moment. Yes, but okay. You can see here from the left Professor Oleg Borisovich Lupanov. He was the dean of the Faculty of Mechanics and Mathematics. Валерий Васильевич Козлов, he is now the chief of our department, and later he was a leader of the Komsomol committee, and here you can see Андрей Николаевич Колмогоров, Ольга Арсеньевна Олейник, Анатолий Алексеевич Лагунов, he was the rector of Moscow State University at that time, and Николай Николаевич Боголюбов. It is one of the first Petrovsky conference at the beginning of 80s, last century. And now I would like to invite you before our next speaker for a short time to our library, and I'll show you in the chief of our library of the Faculty of Mechanics and Mathematics, and her colleague say a few words about the works written by Petrovsky, Vishek, and Landis. Okay, so we have some brief, but I hope that we can translate our session for you also. Okay.